Thanks for joining me in today's lesson. In this first tutorial, we will be able to describe a geometric pattern and use the three geometric formulas. So now we are in section 11.3 in our textbook, and now we're specifically talking about geometric sequences. A geometric sequence is when we have each term is found by multiplying a constant, the same number. This time we call it R, and it's called the common ratio, or we label it as R. So we multiply the same number to the previous term to get each term. So geometric is multiplying. Arithmetic, what we did last time, is adding. So example 1 says find the next three terms. We have 4 and then 12 and then 36. I know that this is not arithmetic because if it were, we would be adding 8 to get from the 4 to the 12, and then the third term would have to be 20. Since it's not, it cannot be arithmetic. So it looks like we might be multiplying, and we're multiplying by 3, and then we're multiplying by 3 again. So it looks like R is equal to 3. So if we keep multiplying by 3, it says find the next three terms. 36 times 3 is 108. 108 times 3 is 324. 324 times 3 is 972. And we could keep going. And you can see that geometric sequences can get some really high terms really fast. So that's the power of multiplying. When we are writing an expression for the nth term, it gets maybe a little bit trickier. Of course, we're writing a sub n. This is our rule, so we always start with our a sub n is equal to. Now, the thing that we're multiplying by is going to be the same thing every time. R is going to be a base, as opposed to the arithmetic when we found D and that was a coefficient. This time in geometric, when we find R, what we're multiplying by, it will be a base. So since we know that the base is 3, that R is 3, we know that we're going to have 3 raised to some power, 3 to the n. I know that that has to be part of it. But what we want to do, and I'm leaving a space here intentionally, is if we start plugging in a 1 and a 2 and a 3, we'll start having the powers of 3. 3 to the first, 3 squared, 3 cubed. But I want my first term to be a 4. So a little trick that you can do is if you take n minus 1 as your exponent, then when you plug in a 1, your exponent turns into a 0. And any base, no matter what R is, to the 0 power becomes 1. And then you simply have to multiply by whatever the first term you want to be. So that's how you can write the nth term, our little rule, for any geometric. You can put your first term as your coefficient, and you could make the base your R, as long as your exponent is n minus 1. And we'll see that this is actually basically our first formula. But I'll get to that on the next slide. So example 2, let's just do one more. It says find the first 4 terms. If a sub n, we have a new rule. This time it's negative 1/3 to the n power. I know since I see a base, something raised to an exponent, then I know that this is going to be geometric and the R is going to be negative 1/3. So let's find our first 4 terms. I'm just going to be plugging in a 1, 2, 3, and a 4. If I plug in a 1, I get negative 1 to the first, which is just, negative 1/3 to the first, which is negative 1/3, comma. When I plug in a 2, squaring a negative becomes positive, and I get 1/9. And then when I go back to plugging in a 3, since that's odd, I'm going to be back to a negative, and that would be negative 1/27. And then the last one, plugging in a 4, raising to the 4th power becomes a positive, and I get 1/81. So you can see for geometric patterns that you can alternate your signs. And whenever you're alternating your signs, you must have had a negative base. Now these terms, the odd ones, or in this sequence, the odd terms are negative. And the odd terms are negative because the exponent is simply n. Every time I put an odd number in for n, it's going to be a negative value. If I would like to put the even terms to be negative and the odd terms to go to positive, then I would have to do some sort of n minus 1 or n plus 1, so that every time I put in an odd number, I would add 1 to it to get an even number, and then we would have the positivity. But I'm going to take that away since that's not what the problem was. So alternating signs is one kind of giveaway that it could be geometric. So our first of 3 formulas today. This is how to find a specific term for a geometric sequence. You take your first term, and that's your coefficient. You take your r, and that's your base, and you raise that base to the n minus 1 power. Now, of course, according to our order of operations, we have to do our exponent first, get that value, and then multiply by our coefficient. But this looks exactly like what we did on our example 1. Our first term was 4, our base was 3, and we had the n minus 1 power. So that's the first of our 3 formulas today. Example 3, let's find the 15th term. Let's use our formula that we just learned. The 15th term, if the first term is 20 and r is 1.05. So if I'm looking for the 15th term, that means that I'm using this symbol, a sub 15, and let's just plug into our formula. The first term, which we are given, that's 20, that's our coefficient. We need our base, which is our r, which we have, which is 1.05, and we're going to raise that to the n minus 1 power, but since I know that n is 15, it's the 15 minus 1 power. Now I know you're probably just going to plug this right into the calculator, and I of course encourage you to do this simple math in your head and make this a 14 when you plug that into the calculator. And I know that this is actually rational, but the calculator cannot convert it to a fraction. You can try all you want, so I'm going to put the approximate. It's approximately 39.599. Now, since this is the 15th term, you might have assumed that it was going to be very large, but 39 is not much larger than where we started with 20, and it's because r is not that much bigger than 1. If r is very big, like a 3 or a 4 or a 5, then your terms are going to get very big. But if r is just a little bit bigger than 1, then yes, you're still going to be going up because multiplying by a little bit bigger than 1 is still increasing, but not that much. If r is something a little bit less than 1, then we'd actually be getting lower from 20 all the way down to, I don't know, 5. If r is equal to 1, well, then your terms are not actually changing because you just keep multiplying by 1. So it all depends on what r is, if it's greater than 1 or if it's less than 1. All right, let's keep going. So example 4 looks very similar to one of the ones we did on arithmetic day. This time we have a geometric sequence. We know that the 4th term is 125 and that the 10th term is 125/64, and we're asked to find the 13th term. So what I did last time is I kind of drew a picture of this, and I'm going to continue to do that. So here's my first term, here's my second term, third term. My 4th term is 125, and then 5th, 6th, 7th, 8th, 9th. My 10th term is 125/64, and I might as well keep going. The 11th, the 12th, the 13th. This is the one that I'm looking for right here. So here is a picture of our geometric sequence, and we need to figure out, basically we need to find r, because once we know what r is, we could just multiply it a few more times and we'll have our answer over here. So what we did with arithmetic was we figured out how far did we add to get from term to term, and then we divided into how many spaces we had. Obviously, that's not what we're going to do for geometric because geometric is multiplying. We need to figure out what we're multiplying by to get from this to this. So ultimately, we're going to be dividing backwards. But then what are we going to do with however many spaces we have? We're not going to divide again because division will equally space in terms of addition. What can we do to equally space for division? And that is a radical. So what we need to do is set up a big radical. The radical is going to have the value that we need underneath it, and that is going to be found by dividing these two things backwards. But then which radical is it going to be? It's going to be the 10th term that we have take away the 4th term. So it's going to be, in this case, a 6th root. So we're going to be talking about a 6th root of 125/64 divided by 125. Again, we're dividing backwards. Which leads me to think about something else that I wanted to add in here, actually right back at here. Sometimes people have trouble finding what R is. If you ever have trouble finding what R is, you can always take any two consecutive terms and divide them backwards. So sometimes R is not as obvious as what D was in the in arithmetic. So you can take any two consecutive terms and divide backwards. So if you had trouble figuring out what R was for example 1, you could take any two terms, 108, and divide backwards from 30 by 36, or 36 divided by 12, or 324 divided by 108. So that's how you can always find R if you need to. Okay, so let's go back to the problem at hand. So we're taking the sixth root of this division. So we're going to be finding the value. So this is like the number of spaces in between our terms, and that's what determines our radical. And the value is just dividing our terms backwards. So let's see, we've got some math to do over here. So 125 over 64, instead of dividing by 125, I'm going to multiply by its reciprocal. And then I can see that the 125s actually will cancel away, and I'm going to get 1/64. So we're talking about the sixth root of 1/64. And this actually is a perfect sixth, because 64 is 2 raised to the sixth power. So the sixth root of 1 divided by 64 is 1/2. And that is what R is. We must be multiplying by 1/2. Let me show you another way to figure out this problem. We don't know what this next term is, but we do know that whatever R is, 125 times R would be the next term. And then multiply this by R, and we'd have 125 R squared would be this term. And then 125 R cubed, and then R to the fourth, and then R to the fifth. 125 R to the fifth, and then the next one would be 125 R to the sixth. So if I come over here and say that 125 times R to the sixth equals that 125/64, then I have an equation that I can use to go and solve for R. The first thing I would do is divide by 125, which is exactly what I did over here in this work. And then I'll have R to the sixth equals 1/64. And then to find R, I would be taking the sixth root of both sides, which is exactly what I did over here. So the sixth root of that would be 1/2. So this is another way that maybe makes more sense for some people to figure out what R is. Okay, so we're not finished. We found R. Let's see if we can continue on and find what a sub 13 is. So we just need to keep multiplying by 1/2. And multiplying by 1/2 does not change the numerator, so it stays 125. The denominator gets multiplied by 2. So 128 is my next denominator. And then 256 is my next denominator. And then 512 is my next denominator. And that appears to be the answer that I'm looking for, a sub 13. But I'd like you to pause the video and tell me the other number that could be the acceptable value for the a sub 13. 125 over 512 is not the only correct answer. Why don't you pause and give some time to think about what else could be a correct answer. Pause now. So what we've forgotten to do, when you take an even radical, when you put an even radical onto your work, don't forget your plus or minus. Don't forget your plus or minus over here. We could be multiplying by a positive 1/2 and get positive 125 over 512, or we could be multiplying by a negative 1/2 and getting a negative and then a positive and then a negative. Plus or minus 125 over 512 is actually the correct answer. Either one of those. We didn't know because we were given two even terms. So because they're both positive, we didn't know maybe the odd terms were negatives in this one because the geometric can alternate signs. So that's a good problem. Go back and watch that if you need to. Let's look at our last two formulas. First, we're going to talk about the sum formula for a finite geometric series. Again, finite means that it stops. So that's again another big S sub n. And in this case, you need your first term, and then you're going to multiply that to this big fraction. 1 minus r to the n power divided by 1 minus r. And put that all in parentheses. This is how you find the sum for a finite geometric series. Now understand that this numerator is not the same as this denominator. There's no common factor to cancel away. This has r to the n power in the numerator. But also watch out for your order of operations. We'd be doing our exponents first, and then we can do our subtraction up here and subtraction down here, and then our division, and then finally our multiplication. So let's find the sum for this. I know that we're talking about a sum because I see the word sum there, but I also see the sigma notation. That means we're adding up a bunch of terms. How many terms are we adding up? Because we need to know that. That's what n is. And in this case, we're counting up from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there must be 12 terms. We also need to know what the first term is, so we might as well plug in a 1 and see what happens. When I plug in a 1, I get 4 times 0.3 to the first power. I'm going to be adding multiple terms to that, but I don't really care what these other terms are. I really just need the first term to use this formula. And this would be 4 times 0.3, which is 1.2. Again, there's multiple terms out here, but I don't need to find them. So I've got a sub 1. I also need to know what r is. I'll put that in a different color. We know that r is always that base, so r is 0.3. And I also need to know what n is. And we know that n, as long as we're starting by plugging in a 1, we know that n is that top number, 12 in this case. So now we have enough to plug into our formula. So we're talking about s sub 12 is equal to our first term, which we found was 1.2, times 1 minus our r raised to the 12th power, divided by 1 minus our r again, our r. Plug that into the calculator, and I believe we get another estimate. The calculator is not able to to put this into a fraction form. About 1.712. I'm using my approximate so that everybody knows that this actually is an approximation, that this decimal goes on for a little bit. So that's how we can use this formula. This is for finite. It's geometric series that stop. What about an infinite? What about an infinite geometric series? Now, it might seem crazy that we can actually add up infinite terms, but it is true. There is a condition, of course, but I'm going to call this S sub infinity, adding up infinite geometric terms. And it's a pretty simple formula. All you need is the first term, which is kind of nice because we can't find the last term, of course. Yep. And we'll divide that by 1 minus r. That's the formula. Of course, it comes with this little restriction. The value of r has to be less than 1. I say the absolute value. I don't care if r is positive or if it's negative, but its absolute value has to be something less than 1. If r is something that's greater than 1, obviously each term will get bigger and bigger and bigger and bigger, and the sum would not exist if we just keep going forever. But if r is something that's less than 1, then the terms are getting tinier and tinier and tinier, and if they go on for infinity, we can actually add them all up. So this is our formula, both parts. So it does, again, it has a condition. We can only do the infinity sum if r is something less than 1. So this base, since it's 0.6, that's something less than 1, and we can add all of these terms together. I don't care that there are infinite terms. We can use this formula. Let's start to see what these terms actually are. I have to plug in a 1 and a 2 and a 3 and a 4 all the way up to infinity, which obviously I'm not going to get there. But if I plug in a 1, 1 minus 1 becomes 0. The base to the 0 becomes 1. So my first term is 4 times 1. And my next term, if I plug in a 2, I'd have 0.6 to the first power times 4 is 2.4. And then if I plug in, let's just do one more. If I plug in a 3, I get a squared power. So 0.6 squared times 4 gives me 1.44. Okay. Obviously, these numbers are getting smaller and smaller and smaller, and I say that they do have a sum, and we can use this sum formula. Actually, let's label our parts first. I know that our r is right here, 0.6, and I know that our a sub 1 is right here, it's 4. I already found it right there. So I can use my formula. S sub infinity is my first term, 4, divided by 1 minus 0.6. So let's do this math. 1 minus 0.6 is 0.4, and 4 divided by 0.4 is 10. All of these numbers, forever, 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 actually add up to 10. Now that might really freak some people out, that they actually can add up to be a simple number like 10. So let me show you an interesting way of hopefully proving that to you. Let's take a different problem. I'm going to just cut it off over here. Let's say I wanted to add 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 and keep going. And I just keep cutting things in half. Now, obviously, this is an infinite geometric series. I'm multiplying everything by 1/2, and 1/2 is something that is less than 1. So I should be able to use this formula. So let's look at it visually. Well, let's actually use the formula first. Let's see what S sub infinity is equal to. It's equal to my first term, which is 1, divided by 1 minus my r, which is 1 minus 1/2. So I get 1 divided by 1/2, it equals to 2. I say all of these fractions will add up, all of these numbers will add up to 2. And let's see if I can prove that to you visually. So I'm going to draw a square. I'm going to try to draw a square at least. So here's a square. Hopefully you can at least believe me that I'm trying to draw a square and that you've seen a square before. So let's assume that that actually is a square. And let's make the area of this square 2. I'm sure that you've seen a square that has an area of 2 before. So what I'd like to do is take that area and cut it exactly in half. If I cut that area in half, then 1 unit would be here and the other half of 1 would be here. But I'm not going to use that 1 yet. I'm going to cut that area in half. So that 1 has been cut in half, leaving half of it here and the other half here. But I'm going to take that half and cut that in half, leaving 1/4 here and the other 1/4 here. But I'm going to take that 1/4 and I'm going to cut that in half. And I'll have 1/8 and the other 1/8. But that 1/8 is going to cut in half. And then that 1/16 is going to cut in half. And that 1/32 is going to cut in half. And I'm going to keep cutting in half and cutting in half and cutting in half and cutting in half. And hopefully you agree that I'll never be able to stop cutting things in half, but yet I'll never be able to get out of this corner. So adding all of these numbers together will indeed equal to 2. It's pretty crazy, but it's true. So thanks for watching this tutorial, and we've got one more tutorial to set you up for our practice for next class. Thanks for watching this one. See ya.